Like Minitab 19 is like the official software is recommended, but you can do like Minitab 20, Minitab 21. They're also available. But basically their functions are kind of similar and doesn't matter too much. So then I have the section recorded, and then I will share my screen of my Minitab setup, and so I am not able to like pay attention to like your raising hands or something. So if you have like any question, just unmute yourself and ask. Okay. Right, so can you guys see my screen right now?
Yes.
Okay, perfect. Oh. Okay, so for the first task, you're gonna generate or like simulate 10,000 data from an exponential distribution. The way to do that is first you click on calc, and then you go to random data, and then you find exponential. So basically this function asks you to like helps you to like generate random data from all kinds of like common distribution. In this case, you have like even like not that common distribution, like Cauchy distribution, like gamma distribution, like Laplace distribution, but we don't have to use like those sort of complicated function. So we just click here exponential. We're gonna generate 10,000 random variables. I think that's required in your homework, and I'm gonna store that in column C1, which is the first column, and I have their scale. So basically, that's the meaning of parameter. Like if you remember the general format of an exponential distribution is like e to the power of minus lambda to x, or e to the power of minus lambda t, and that lambda is your parameter. And by changing or by adjusting that parameter, you can achieve a exponential distribution with different mean and variance. And in this case, I just need a exponential distribution with mean equals 1 and variance also equals 1. You have some formula to calculate the mean and variance, but generally when your lambda equals 1, you have an exponential distribution with mean 1 and variance 1. So when I click on OK, I have 10,000 numbers distributing on my like C1 column. And first I can draw like a histogram of the 10,000 number. So the graph variable, I double click C1, which means I'm gonna draw like a graph where my x-axis is all the numbers from the C1 column. And when I click on OK, here's my histogram. And so you notice it's pretty exponential, like it's pretty much an exponential distribution. Notice our mean is pretty much 1, so that means if you find 1 on your x-axis, which is like a little bit on the left of 1.2, your label 1.2, it's a little bit on the left of that, you have 1, and that's the mean, meaning the area on the right of 1 and on the left of 1 should be equal. And in this case, notice my first column the 0, 1, the first column is not like it's kind of strange, right? So because for exponential distribution, it's sort of monotonic, like you expected to find very like a very high percentage of number on the left than on the right. But here, your first column actually is not as high as your second column or your third column, right? So that's kind of strange. And that's because the first column consists of number between like minus 0.05 maybe to positive 0.05. So notice that 0 here is on the middle of the first bar. And because we cannot generate any negative number from exponential distribution, so basically that means we lost like half of the number. Like if you draw like a histogram starting from 0 instead of in my graph it's starting from a negative number. If you start from 0, then your first bar should be the highest and followed by the second bar, the third bar, etc. But in this graph, since I'm not adjusting my x-axis, I'm not starting from 0, so it looks a little bit strange. But it doesn't matter too much, right? Because the general trend, the overall trend, you should discover it's pretty exponential. Then we're gonna plot them in a QQ plot. I think it's on graph, probability plot. So we plot our C1 column, our exponential distribution, against a normal distribution. That means we compare our distribution with a normal distribution. So here, I think you should like choose a normal distribution. C1. And basically this is our QQ plot. I think from the class you learned, like if the blue line is kind of coincides with the red line, then that means my distribution, which is the blue line, is like approximately a normal distribution. But here you see like it's a very large bending curve. It has a very heavy tail. And to interpret this graph, right, we first look at the red line. Remember our generated distribution has a mean of 1, right? So if I look at the x-axis, the horizontal axis, and I locate 1, which is somewhere between like 0 and 2.5, right? If I locate 1 and I go vertical up to find the intersection point of 1 and the red curve, I should discover like 50% because the red curve symbolized the normal distribution. And if I have a normal distribution with mean 1, that means I should discover 50% of the data below 1 and 50% of data above 1. So if you like look at the 50% and you look at the red line, then the intersection point, its horizontal axis should be 1. And the x-axis, the number suggests the standard deviation, right? So in this case, the red line, if you look at minus 2.5 and plus 2.5, that is the number you're gonna find between 2.5 standard deviation away from the mean. So in this case, my mean is 1, right? So if if we look at like 5.0, the x-axis, the 5.0, that means I'm 4 standard deviation above the mean because my mean is 1, right? And standard deviation is also 1. And if you look at the red curve, the intersection of 5 and that red curve, you see its horizontal like percentage point is around 99.99%. So that means I should find, like given a normal distribution, I should find like more than 99.99% of the data, which is below like 4 standard deviation above the mean. So if I have a normal distribution with mean 1, then 99.99% of my data should be less than 5. That's like what's the meaning of the red curve. So basically the red curve is a benchmark. It shows what should happen if I have a normal distribution. So if I plot my own distribution, which is a red line, against my own distribution, which is a blue line, against this graph, then if my blue line doesn't coincide with the red line, then I would say maybe my distribution is not a normal distribution. And in this case, my distribution is actually an exponential distribution, which is very different from the normal distribution. So you see the blue line actually derives very far away from the red line. So we're gonna go to the second part.
Victor,
Yep.
can you record the meeting?
Yeah, I'm recording.
Okay, thank you.
So I see a question, can we use score instead of percentage? Think percentage is the best. So basically this plot is a transformation from the z-score table, right? Instead of looking at that table, which is very hard to look at, which is very hard to compare, you plot it, right? So your y-axis, your vertical axis, the percentage part is actually like some number from the z-score table, but it's not like only 5%, 10%. I think on our z-score table, you only have several like cut-off percentage, alpha like 5%, 95%, right? But here you have like 99.99, you have 99, you have 95, or sort of thing. So you can find out like the vertical axis, it's actually not equal distanced, right? Because in like a normal distribution, like your z-score table is not equal distance as well, right? There's a huge amount of data clustering in the middle, like from 99% to 1%. There's a like the majority of the data, perhaps like majority of data lying in the middle, and you have some outliers. For example, you have some 3 standard deviations away from the mean, but you shouldn't discover a lot of that kinds of data. So basically, by using the QQ plot, we kind of strategically change like the distance of the y-axis to make our red line a straight line. That's how you achieve like a straight red line. If you use like score instead of percentage, then probably you cannot do the not equal distance adjustment. Like if you have different scores, you like empirically you have to like draw the y-score with equal distance. Like you have a 10 and 9 and 8 and 7, right? Those distance should be kind of equal, and the red line should not be straight, should be bending. In this case, you shouldn't. In this case, because um, we are not a standard normal distribution. The QQ plots are plotting like a normal distribution with mean 1 and standard deviation of 1. So if you want to find the 1.5 standard deviation away from the mean, you should use 1 minus 1.5 and then 1 plus 1.5. So that should be like negative 0.5 to 2.5. That captures like 1.5 standard deviation from the mean. All right, so for the sum of two exponentials, that basically that's the simulation of the central limit theorem. Like from this graph, we see the exponential distribution is very different from the normal distribution. We can look at this QQ plot. We can also looking at this histogram, right? A normal distribution represents a bell curve, kind of good looking and symmetric. But here you have like a monotonic decreasing probability density function. That's very different from the normal distribution. But according to the central limit theorem, if I have like a large number of exponential distribution or some other distribution, for example, binomial distribution or uniform distribution, right? As long as I have a large number of them and I sum them up, then my final distribution, like my resulting distribution, should be approximate to a normal distribution. That's what central limit theorem says. And we are here basically to do an experiment to like technologically prove the central limit theorem. So the way I'm doing this is I'm gonna generate like another calculator. I'm gonna generate like another 10,000 random data from exponential distribution. And by the way, those two exponential distribution, they have to be independent because I'm just generating numbers from the exponential distribution with requirement that their mean should be 1 and standard deviation should be 1. But all the numbers are generated randomly by this computer, by some advanced algorithms. So they're pretty much independent from each other. So I can generate like another 10,000 data from the exponential distribution. If you graph them, you should pretty much see similar things. So it's also exponential distribution, pretty much like the previous one. However, if I sum them up, so I go to calc and the first one, calculator. So I want to store them into the third column. Actually, I can name them. Well, forget about it. Never mind. So I store them in the third column, and the thing I'm gonna calculate is the sum of C1 and C2. So I just add them up. I click OK, and here in my third column is a sum of the two exponential distribution. I think that's one of your homework problem. You're gonna do this. If I plot them, so I plot the third column. You see, this distribution is kind of different from exponential distribution. Remember, the exponential distribution is monotonically decreasing. But here, although you have like a trend, you have like it is bending to the right, um, but it looks a little bit more symmetric than the previous one. So if I go to the previous one, that's that's the exponential distribution, a pretty standardized exponential distribution. And the C3 is a sum up of two exponential distribution. It actually has a name. I think it's called like Laplace distribution or something, but it's like its probability density function is very complicated, and we're not gonna discuss that. But the bottom line, like the takeaway from this is like when you sum up like two exponential distribution, then it looks more normal, more symmetric, more like a bell curve. And basically that's what central limits theorem tells us. And I'm gonna do like 10 exponential distributions and sum them up. So by the way, when you like hand in your homework, I think the best way to do this is to take a screenshot and maybe paste them into a Word and something and transfer that to a PDF file so I can grade them easily. So here the Laplace distribution, I think, is basically the name of the summing of two exponential distribution, and you get a Laplace distribution. So here basically I have 10 independent exponential distribution with parameter 1. Then just like what we did, we're gonna sum them up for new distribution. So I store them into column 11. The expression is just summing them all up. So then I have another like 10,000 numbers. And each of the numbers are the sum of 10 independent, independent exponential distribution. So here, something magic would happen if you plot the histogram of the C11 of the resultant distribution. If you look at the histogram, it looks pretty normal, right? So I think in class you learned if you like sum up 30 or like 50 sort of exponential distribution or some like binomial distribution, then your resulting distribution would be approximately normal. But here, by doing simulation, you could see when you sum up 10 exponential distribution, it really looks pretty like normal, pretty like a bell curve, right? We are like our individual distribution, the starting distribution, has a mean of 1 and standard deviation of 1. Here, because I'm summing 10 up, right? So you should expect the resulting distribution with a mean of 10. And here you do, and a variance of 10, right? Because they're independent. If you remember your homework 3 or something, or homework 3, I think, you're summing them up, and the variance of like a plus b equals to the variance of a plus the variance of b, considering they are independent. So the variance of this final distribution is expected to be 10, and the standard deviation should be the square root of 10, approximately 3. And you can check that, right? The mean should be 10, and here you see you have like a 10.5 in your x-axis, and the mean should be a little bit less than 10.5, and it should be pretty like symmetric with a standard deviation of a little bit more than 3. And yeah, because you have like a mean of 10, and if the standard deviation is 3, then the two standard deviation from the mean should be in the range of 4 and 16. And if you like locate 4 and 16 in the x-axis, it basically contains like 95 or even more of the numbers. So although this graph looks still like a little bit bending towards right, but you see you can compare this with the sum of the sorry, I delete that. You compare that with the exponential distribution, and that's a huge difference, right? So in real life, when you have like 10 exponential distributions and you sum them up, it's very safe to like approximate your resulting distribution with a bell curve, and it's pretty safe to use the z-score table or like any property related to normal distribution very safely.
Could you please show how to draw the QQ plot against the histogram of C11?
Okay, of course. So I go to graph, I go to probability plot. So that's how we draw the QQ plot. QQ plot is actually another name of a normal probability plot. So for probability plot, I can create like the benchmark for all kinds of distribution. Here I click on distribution. I can draw my distribution against a normal distribution, against a log normal distribution, against a gamma distribution, against an exponential distribution, right? So here's my benchmark. And QQ plot means my benchmark is against a normal distribution. So basically the probability plot is like a bigger concept. You can draw your own distribution with all kinds of distribution to compare if your distribution is actually one of the benchmark. In the homework, I'm gonna draw my distribution with a normal distribution, right? To check if my distribution actually coincides with a normal one. So and that's still the C1, right? That's the column 1. So actually I do something. So if I draw my, so basically the C1, the first column, is the simulation of an exponential distribution, right? It should be very exponential. But if I don't know, like am just given those 10,000 data, I don't know that's a simulation from an exponential distribution. I don't know that, and I want to check if that is a normal distribution. Then I plot my own distribution against the normal distribution. But after that, I see that there is a bending curve, which gives me some evidence that my distribution might be actually exponential instead of normal. So I could actually plot my distribution against an exponential distribution. And this is not a QQ plot, because the QQ plot, you always compare your own distribution with a normal distribution. That's a QQ plot. But here, I'm introducing like a bigger concept. You can actually compare your own distribution with any kinds of distribution. In this case, we're comparing my distribution with exponential distribution. And if you see that, you would pretty much anticipate your blue curve and the red curve actually coincides a little bit, like for the majority of the places it coincides. And if you see this graph, it pretty much very huge evidence for like my own distribution is actually an exponential distribution, which we know it is because we generate our like 10,000 data from exponential distribution. So put that aside, let's do the homework. Probability plot. We're gonna plot the 11th column, which is the sum of 10 exponential distributions against a normal distribution. We want to check if our new distribution, our resulting distribution would look normal, approximately normal. And we already have some evidence from the graph I just showed you, right? Pretty symmetric, kind of symmetric at least, and with a proper mean and standard deviation. So if I click on OK, this plot still looks bending, right? It has heavy tails. So I cannot actually conclude like my resulting distribution is like normal because it doesn't coincide pretty well. But if you compare this with our first time, like with the first column, then you see like a huge difference. So basically, the sum of 10 exponential distribution is pretty much more normal than one exponential distribution. And that's all like I want you to take away from this session. And your homework, I think you still need to do like you sum up 2 and then you sum up 5 and finally you sum up 10. So you should so the histogram should looks like more and more approximate to the Bayes curve. And that's the point. For your second question, I don't have your data, but for financial data, like it actually coincides with the red line even more closely. But a problem with financial data is if you like plot them into a histogram, it should look pretty symmetric and very likely to a Bayes curve, but it's not a normal distribution. Like I would say like 99% of the financial data, they're symmetric, but they have heavier tails than normal distribution, or we call that a leptokurtosis. And that means we generally discover like more outliers than normal distribution. Our tails are heavier. In a normal distribution, we're not gonna find too many observations, which is like 3 standard deviations away from the mean. But in financial data, we do. Like the stock return, right? You have a mean of approximately 0. That's the characteristic of a stock return. The mean should be pretty much equals to 0, but you have a very high like standard deviation. Like you're gonna observe some outliers pretty often, more often than that of a normal distribution. So we have like a whole branch of subject called risk management in financial industry. Basically, that's what they do. They're gonna model like the heavy tails of the financial data to make some rational decisions. So I didn't do the problem number 2, but if you plot that data, you should anticipate a pretty symmetric histogram, but that doesn't mean your distribution is normal. So sometimes the histogram would lie to you. Like this histogram, although it looks pretty symmetric, actually in this case it's not very symmetric. It's still like bending towards right, because we sum up like 10 exponential distributions. But the more accurate way is to plot your data in a probability plot and to see if the red line and blue line coincides. And your homework problem 2, I think you should find the majority of the places like the blue line and the red line coincides, but in the tails, like for the outliers, which is like a very like I think 5 or 4 or 5 standard deviations away from the like below the mean or above the mean, and in that segment you find like more observations. That's a characteristic of financial data. So first, how to copy data into Minitab? I think you just copy and paste. You, you just copy, like I think you have like a Excel Excel spreadsheet or something, right? Doesn't work. Let me think. Yeah. I think basically copy paste works. To put the appropriate breaks in the graph, basically that means your x-axis, right? But I think like this plot looks pretty good. I don't think you have to like change anything in the x-axis. It breaks down your distribution into some tiny small rectangles, and I think this looks good. So you don't have to like change the interval of the x-axis. And for the second problem, what happened? Let me see the question. What happened when the lowest daily return was observed? I think it happens on like 1987. I might be wrong. It happened on 1987 or something, and it's called Black Monday. You can just Google Black Monday, and that day like it's it's kind of a tragedy. Like SP 500 decreased by around 10%. I don't know. I might be wrong, but I can do it now. Yeah, the Black Monday happens 1987. Oh. Yeah, the market decreased by like more than 20% in that single day. And So for normal distribution, like basically you do not anticipate like that much a decrease, like minus 20. Like when you have like a mean, which is close to zero, that is your market return, your stock return as a whole. The mean should be pretty much close to zero, and you have a standard deviation of a few percent, like 1 or 2%. And then it's hard to imagine like in a single day the market could go down by 20%, which is more than 10 standard deviations from the mean. uh, so that could hardly happen if you have a normal distribution. But the stock market, it is not a normal distribution. As I said, it has a heavier tails. So, and it happens in history. It happened in history, 1987. Um, so that's why we're gonna do risk management. Like you go to investment banks, basically all investment banking and other companies, they have like a risk management department. Um, and the stuff, they basically do things like this to model the risk.
So then for the homework, should we just type up a synopsis of Black Friday and say it moved more than X times the standard deviation, or how should we actually answer the question?
Yeah, basically.
Thank you.
You guys still have difficulty like importing the data? Basically, the like copy paste just works for me. Um, like if not, I Not quite sure. Share my screen. So I think if like copy paste doesn't work, still we have like some way to import the file. So I go to I go to my files. Maybe not this one. I go to temporary files here. No. Oh yeah, here. I go to here my file and temporary file, and I can upload files. So basically, I have like stock return data, and I upload the files to this environment. Oh, and it succeeded. And then I go to temporary files. I click on NYSE, and then I double click. It asks me how to like open this file, and I can do the Minitab 19. And yeah, it's here. So yeah, that's how you copy paste. Like if you have like you guys have a chat group and somebody like raise questions about how to import data, you could tell them like to watch my recordings like at about like 55 minutes time. Here's how you import your data. Yes, like for the homework, you just take a screenshot and paste your graph and leave some comments, right? You cannot just submitting 10 graphs to me. You have to leave some comments to let me know like you understand what you are doing. How to insert a histogram? I'm not inserting a histogram. I just because I have my data like C1, C2, I have those kind of data, and I can click on graph. I can plot them. I can plot them in the histogram. And in your homework, I think you just maybe take a screenshot of this histogram. You can zoom them a little bit to make it like a little bit smaller to make a screenshot. You can also like I think you can also maybe I don't know if this works like copy graph, or you can send the graph to like a Word document and print, or I didn't use those functions, but you can try them out. So and by the way, like for the second half of the semester, you're gonna use Minitab pretty often. Like in regression analysis, you cannot do all the calculations by hand because you have so many data points, like maybe a couple hundreds data points, and you do some and all the calculation, all the formula involves like a summation sign. So basically, you're gonna sum like something several hundreds of times. So it's not very practical to be done by hand, and you're gonna use Minitab repeatedly. And I'll go over like how to do a regression analysis when you have like those kind of homework. Any questions?
I'm just gonna ask since I came late because I just had class. If you already answered the question, it's alright because I can just go to the recording. But you discussed a little bit about the sum, the 10 sum, correct?
Yep.
And the histogram and how it changes, correct?
Yes, I did that.
Okay, cool. Then it's okay.
Thank you. Do you need to change the labels from the midterm to cut point? I think no, you don't have to change that. The SIG can ask us to analyze the. I think you should do both. You should do both histogram and QQ plot, and basically like when you have like a unknown data set, the first step is to plot them into a histogram, because you can see like a general distribution, the general trend of your distribution. But as I said, in this case, when you plot them against a histogram, you're gonna be pretty convinced that this data comes from a normal distribution, because it should look pretty symmetric and pretty like a bell curve, pretty normal. But the histogram might lie to you, and in this case, you have like a heavy tails, both below the mean and above the mean. So since you have heavy tails on both sides, so it still looks pretty symmetric, but it's not a normal distribution. You have heavier tails than normal distribution. So the first step is to plot them in a histogram, and that might give you some evidence. Like a histogram looks like an exponential distribution, then you might use some exponential model to analyze your data. If your histogram looks more like a normal distribution, then you might use some normal distribution model to analyze your data. And for the second question, obviously, when you plot your stock return data into a histogram, you'll find it's more like a normal distribution. But that might lie to you, so you're gonna then utilize the QQ plot to see if your blue curve actually coincides with the red curve. And in your homework problem, it shouldn't coincide very well. It should coincide well in the middle point, in the middle section, but on two tails, it shouldn't coincide pretty well. Any final questions? All right, good luck on the homework. I'll upload the recording as well as possible. What should we put in? The variable is just the column, like here, from column 1 to column 10 are my simulated 10,000 data from the exponential distribution. If I want to plot like a histogram of my first simulated data, which is my C1 column, I just go to graph and histogram, the simple histogram, okay. And here in the graphing variable, I just double click C1, and that means I have 10,000 data going into this program, going into this algorithm. And I click on OK, I got like 10,000 data from the C1 column. And the same applies to like later when you're gonna sum up like 10 exponentials.